Hello guys, this is Daniel Andrew.
And Jonathan here.
We will be building a self-balancing robot. See you guys. First part of self-balancing robot is assembling the components. So building a self-balancing robot starts with preparing and assembling all of its major components into a stable structure. So in this project, the robot was designed using a compact two-wheel chassis with multiple acrylic layers to organize the electronics efficiently. So the assembly process began by attaching the geared DC motors on both sides of the chassis, ensuring that they were tightly secured to prevent unnecessary movement during operation. So since the robot relies heavily on balance and precision, keeping the frame stable and symmetrical was an important step. So after installing the motors, the wheels were carefully attached to the motor shafts to ensure proper alignment and smooth rotation. So since a self-balancing robot continuously adjusts its position to remain upright, even small misalignments in the wheels can affect stability and movement. So the frame was then assembled layer by layer using spacers and screws to create enough space for the electronics while keeping the robot lightweight and compact. So the next step involved mounting the main electronic components, including the microcontroller board, motor driver, and sensor module. The upper section of the robot was used to hold the control system, while the lower layers provided organized placement for wiring and supporting components. So proper spacing between components was important to avoid interference and to make troubleshooting easier during later stages of development. So throughout the assembly process, careful attention was given to positioning and organizations, since the robot constantly shifts and balances itself during operation. Having a strong and properly assembled frame contributes greatly to overall performance. So at this stage, the robot already began to resemble a functional balancing system, even though it is still required proper electrical connections and programming before it could operate independently. So this part is the wiring of all components. So here is the circuit diagram of the self-balancing robot. Once the physical assembly was completed, the next important stage was wiring all the components together. The robot uses a microcontroller as the brain of the system, a motor driver to control motor movement, geared DC motors for mobility, and a motion sensor responsible for detecting tilt and orientation. So proper wiring is one of the most critical parts of the project, because even a single incorrect connection can prevent the robot from functioning properly. So the motor driver was connected to the geared motors to provide controlled movement based on commands from the microcontroller. So since the microcontroller alone cannot supply enough current to drive the motors directly, so the motor driver acts as an interference between the controller and motors. So each motor was connected carefully to ensure that forward and backward motion could be properly controlled during balancing adjustments. So the motion sensor, which is responsible for detecting the robot's angle and movement, was then connected to the microcontroller using communication pins. So this sensor continuously measures changes in tilt, allowing the robot to determine whether it is leaning forward or backward. Accurate sensor readings are extremely important because the robot depends on this information to immediately correct its balance and prevent failing. So finally, all power connections were organized and secured to reduce loose wiring and maintain a cleaner layout. Proper cable management was necessary not only for appearance, but also to avoid accidental disconnections during movement. After verifying all connections, the wiring stage was completed, making the robot electrically ready for programming and testing. In this part is the coding for the self-balancing robot. So after assembling and wiring the self-balancing robot, the next important step is decoding the system so that the robot can actually balance on its own. So the program serves as the brain of the robot because it tells the microcontroller how to process information, interpret sensor data, and control motor movement. So during this stage, the coding process begins by setting up the microcontroller and initializing the sensor module responsible for detecting tilt and movement. So the proper setup is necessary because the robot relies heavily on accurate measurements to maintain balance. So the next part of the coding process involves calibrating the motion sensor so it can properly detect the robot's positions and orientation. So since the robot continuously shifts while trying to remain upright, even small errors in sensor readings can affect performance. So the sensor constantly measures the robot's tilt angle and sends this information to the microcontroller. So through coding, the robot learns to identify whether it is leaning too far forward or backward and prepares to make immediate corrections. So once the sensor data is successfully collected, the program continuously calculates the robot's movement and determines how the motors should respond. If the robot leans forward, the motors automatically rotate forward to reposition the robot underneath its center of gravity. Similarly, if the robot tilts backward, the motors reverse direction to restore balance. So this balancing process happens repeatedly and very quickly within milliseconds, making the robot appear as though it is balancing naturally on its own. So to improve the robot's stability and responsiveness, the coding process commonly uses a PID control algorithm. PID, which stands for proportional, integral, and derivative control, helps the robot determine how much correction should be applied depending on the tilt angle and movement behavior. The proportional part responds to the current error, the integral part considers previous accumulated errors, and the derivative part predicts future movement to reduce sudden instability. Through proper tuning of these values, the robot becomes smoother, more stable, and less likely to wobble excessively. In the first try, after running the code, we observed that the robot isn't working. So we realized that the main problem is the values of KP, KI, and KD, the gains of the PID controller. Here are the clips during adjusting the values. So what we did actually is adjust the values of KP, KI, and KD. After adjusting, here is the stabilized robot. So after spending a lot of time adjusting the values of KP, KI, and KD, we finally started seeing real improvements in robot's performance. So compared to our first few attempts, where the robot would immediately fall or shake uncontrollably, so this time it was noticeably more stable. Seeing the robot finally stand and respond properly felt really satisfying because it showed that all the testing and adjustments were slowly paying off. It honestly became one of the most rewarding moments of the whole project because we finally saw the robot doing what it was actually designed to do. So one thing we realized during this process is that balancing a robot is not as simple as just uploading code and expecting everything to work instantly. So the robot depends heavily on the PID values because these determine how it reacts whenever it starts leaning forward or backward. So after adjusting the proportional value or the gain, we noticed that the robot became more responsive to movement. It started reacting faster whenever it tilted, which helped it correct its position more quickly. However, we also learned that making this value too high could cause the robot to shake too much, so finding the right balance was important. So the KI value or the gain of the integrator also played an important role in helping the robot maintain stability over time. In this part, we helped correct small errors that kept happening repeatedly while the robot was balancing. So without proper adjustment, the robot sometimes leaned slightly to one side or slowly lost balance after a while. By tuning the KI value carefully, the robot became more consistent and better at staying upright for longer periods. Even though its effect was not obvious right away, we eventually understand how important it was in improving overall balance. At the same time, adjusting the derivative gain helped make the robot's movement smoother and less aggressive. Before tuning this value, the robot sometimes reacted too suddenly, which made it wobble or overrock itself. After making adjustments, the robot's movements became more controlled and natural. Instead of making sharp connections, it started balancing in a way that looks smoother and more stable. This was important because balancing is not only about reacting fast, but also reacting properly without causing unnecessary movement. What made this experience really interesting was seeing how small changes in the code could completely change the robot's behavior. Sometimes, even a slight adjustments in the values produce noticeable results. It taught us that robotics is really a combination of patience, observation, and problem solving. So working on this self-balancing robot project was both a challenging and rewarding experience to me. At first, I honestly thought the project would be straightforward because it only looked like a small robot with a few components. However, as we started to assemble everything and understanding how this system worked, I realized that building this robot project required much more patience, problem solving, and understanding than I initially expected. So this project was not simply about putting parts together, it was about making different systems work together to achieve one goal, which was to make the robot stand and balance on its own. So one of the things I learned during this project was the importance of preparation and proper assembly. Even though assembling the robot looked simple at first, every small detail mattered, and the placement of components and the stability of the frame and the alignment of the motors all affected the robot's performance. So there were moments when times did not fit perfectly or adjustments had to be made, and it taught me that these projects often involve trial and error, and I learned that patience becomes very important, especially when solving unexpected problems during the building process. And in the wiring stage, it also taught me to be more careful and attentive to details. At some point, it became easy to feel confused because of the number of wires and connections involved. I realized that one wrong connection could stop the whole robot from functioning properly. And because of this, I learned the importance of checking connections carefully and understanding the purpose of every component instead of simply following instructions. So these experiences improved my confidence in handling electronic components, and it helped me more organized when working on technical projects now. So for me, the most challenging but also the most interesting part of the project was coding of the robot, and seeing the lines of codes turning into actual movement feel exciting, but at the same time frustrating whenever the robot did not behave as expected, like what we did in the first try. So there were moments when the robot would shake too much, fall immediately, or respond incorrectly, which honestly tested my patience. However, through testing and adjusting the values repeatedly, I slowly understood how coding directly affects the robot's behavior, and it made me appreciate how important programming is in robotics and the automations. So, what made this project meaningful was that the movement when the robot finally started balancing properly, and seeing it respond to movement and maintain stability, and it gave me a sense of accomplishments because I knew that the effort placed into assembling, wiring, and programming finally paid off. So, in this project, it reminded me that success in this project does not always happen immediately. Like sometimes, when we rush things, Sometimes it requires repeated testing and small improvements and learning from mistakes before achieving the expected outcome. The self-balancing robot project taught me more than just technical skills, and it taught me patience, critical thinking, solving problems, like rushing things, and the value of persistence when facing challenges. And it also gave me a better appreciation of how the electrical systems, the mechanical systems, the electronic systems, and coding all work together to create sometimes something functional. And although the project was not always easy, it became a value of learning experience that improved my confidence and understanding as an engineering student, as an electronic engineering student.